Okay, so we're in chapter 3 now. Chapter 3 is a very large chapter for us. I believe it has 11 sections that we're going to cover. And a big part of chapter 3, especially in the earlier part of this chapter, is learning shortcuts to taking derivatives. So where we left off last time was in section 2.8, where we talked about the derivative as a function. And we derived the derivative of a few different functions in the examples for that section, and you would have done more in the homework as well. And we saw that, the process can be somewhat tedious because it involves taking a limit of a potentially complicated expression, which might require a lot of algebraic simplification. And having to do that every single time that we need to take a derivative is ultimately kind of impractical, because usually when we get to applications of derivatives, mostly in chapter 4, the act of taking the derivative of a function is only one small part of a much larger problem. So devoting a whole lot of time to taking a derivative is not ideal. And fortunately, there are several very convenient shortcuts for taking derivatives of specific functions. So that's what we're aiming to do here. In particular, in 3.1, we're going to be looking at the derivatives of polynomials and exponential functions. And I'm actually, even though this is the title of the section, we aren't going to be looking at all exponential functions in general. We're going to be looking at the exponential function, e to the x. And then later on in chapter 3, we'll deal with the more general case of all exponential functions. But let's go ahead and start off here by looking at the simplest types of functions that we can do calculus with, which are constant functions. So let's say that we have some constant function, f of x equals c, where c is just some real number, okay? From the graph of a constant function, we know that it looks like a horizontal line. And a horizontal line anywhere is going to have a slope of 0. So I would expect the constant function f of x equals c, regardless of what c is, to have a derivative of 0 everywhere. And that's based on my understanding of the graph, but we could also be a little bit more precise with that and prove that assumption, prove that that conclusion using the definition of the derivative. So here, let's suppose that, again, f of x, the function we're talking about, is defined as it is up here. It's equal to some constant c. Then what is the definition of the derivative look like when applied to that function? Well, f prime of x would be the limit as h approaches 0 of f of x plus h minus f of x all over h. That's our definition of the derivative. Now, whether you're plugging x plus h or x or anything else for that matter into this function, the output is always the same number, that constant c. So this and this are both equal to c, meaning my numerator now looks like c minus c, which of course is 0. 0 over h is going to also equal 0, and the limit as h approaches 0 of 0, because it's a constant, is just equal to that constant, 0. So what this does is it shows that regardless of what our constant c is, if we're taking the derivative of a constant function, f of x equals c, its derivative is always equal to 0. Using different notation, we could also write this. The derivative of a constant function is 0. d dx of c equals 0. Okay? This is just the same thing as this, f prime of x equals 0, using different notation. Okay? Now that's helpful, but we want to expand our differentiation techniques to larger classes of functions. So the next simplest type of function that we're going to talk about is a power function. And a power function is any function of the form f of x equals x to the n, where n can be any real number at all. It does not just have to be a positive integer. It could be a rational number. So for example, f of x equals the square root of x is technically a power function, because that could be written as x to the 1/2 power. N can be a rational number. It can even be an irrational number. We could have f of x equals x to the power of pi. Now, you may not know how to interpret an irrational power, but that is something that we can make sense of. So we want to be able to deal with these types of power functions. So I'm going to give you the rule here, And if you go back to some of the examples that we did in section 2.8, you can confirm that this was working back then, that this rule, even though we didn't use it explicitly, was showing up back then. If n is a positive integer, then the derivative of x to the n is equal to n times x to the n minus 1. So in other words, when you have a power function, if you want to take the derivative of that function, you can think of the exponent n as coming out to the front, like we're seeing here, and now it's becoming a coefficient on that power function. And then we decrease the exponent by 1 when we do that. So bring the n down and then decrease the exponent by 1. We call that the power rule. We're going to prove that rule. Your book gives 2 proofs using each of the different definitions of a derivative that we gave in section 2.8. I'm only going to talk about the second proof because, in my opinion, I kind of prefer that one. In order to understand this proof, you have to remember the binomial theorem from algebra. Now, I'm not going to do a review of the binomial theorem, but I'm going to point out where it's used. And if you need a refresher on it, you can go to something like Khan Academy or look it up on YouTube. How does the binomial theorem work? So this is the proof. We're supposing that f of x is equal to x to the n, that power function. So when I do my derivative, here's my definition of the derivative. F of x plus h then would be x plus h to the power of n. That's what our function does. Minus f of x, which is x to the n, all over h. Now the binomial theorem shows up here, and this is actually why we needed to assume that n is a positive integer for this specific statement of the power rule. Because when n is a positive integer, this is a binomial raised to a positive integer power, and the binomial theorem gives us a way of expanding that out. So what you're seeing here in square brackets is what the binomial theorem says that x plus h to the n expands out to. Okay? Now, just as a quick refresher, again, I'm not going through the whole binomial theorem, but the coefficients on each of these terms, the things involving these n's here, come from combinations. If you remember combinations and permutations, these are the result of combinations. N choose 0, n choose 1, n choose 2, and so on and so forth. You're not going to need to use the binomial theorem in this section. It's only showing up in this proof, okay? So don't worry about spending too much time reviewing this if you don't remember it. Now, having expanded this out, the goal is to simplify things as much as I can. And I notice that I have an x to the n here and a minus x to the n here. So those, at the very least, are going to cancel out. And then if you notice, all I'm left with are these terms here, all of which have at least one h in them. In fact, if I'm very careful to investigate each term, I see I have an h here, an h squared here. The next term that's implied by this dot 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 would have an h cubed, and then an h to the fourth, h to the fifth. That power increases until we get to h to the n, whatever that n happens to have been. So because all of those terms have at least one h, I can cancel this h with each of those. And because this term here is the only one of these guys that had just one h in it, after cancellation, it's the only term that's going to remain where all instances of that h have been canceled out. For example, this h squared, one of those h's will cancel with this, leaving me an h left over. Same with all of the terms implied by the dot 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 here, the ellipsis. There's going to be at least one h left over in each one of those terms. Now is where we deal with the limit. So the limit as h approaches 0 is being applied to a sum of functions here, and using my my limit law from section 2.3, which says I can bring that limit into each term individually, I can see that every term that has an h in it can be evaluated. The limit can be evaluated by using direct substitution with that 0. So plugging a 0 in for this h will make that entire term go to 0. The next term in here will have an h in it. That term will go to 0. This term will go to 0 because there's an h there. And this term will go to 0 because there's an h there. So that means the n times x to the n minus 1 power is the only thing left after evaluating the limit. And that's what my power rule says. So that means we've proven what we set out to prove. F prime of x is equal to n times x to the n minus 1. Okay? Now again, when we stated the power rule here, we made the assumption that n is a positive integer. But as I said before, by definition, a power function is any function of the form x to the n, whether or not n is a positive integer. N should be any real, n can be any real number, and it's still a power function. And it turns out that the power rule, even though we only proved it for the case where n is a positive integer, actually works for all power functions. So it's restated here, we call it the general version, but it's still just the power rule. If n is any real number, then the derivative of x to the n is n times x to the n minus 1. And we don't have the tools to prove that yet, but we will a little bit later in chapter 3. So what we're going to do is use this rule in its most general form for now, and prove it later when we have the necessary tools to do that. Okay? So let's take a look at some examples. And notice I have 6 functions here that I want to take derivatives of. If I was using my limit definition to do every single one of them, I would be spending a lot of time on this example, because as we've already seen, that's time consuming. But with my power rule, this is a much faster process. Y equals x to the 5th. I need the derivative. It says differentiate the following functions. The derivative looks like y prime. And according to my power rule, all I need to do is in my original function, take the exponent, which is 5, bring it out front, 5x, and then decrease the exponent by 1. 5 minus 1 is 4. And I'm done. Look at how fast that went. If you tried using the limit definition of this thing, you would be spending a lot of time on it because, again, in your limit definition, when you do the f of x plus h right here, we're looking at the function x to the 5th power. X plus h to the 5th power expands to a very big polynomial. So that's a lot of writing, a lot of simplification that we now no longer have to do. And if you think that's bad, this one would be near impossible to do that way. Not near impossible, but it would be an impractical example to try and do with the limit definition. Y equals x to the 100th power. Y prime then is equal to 100 x to the 99th power. Again, I bring the exponent out to the front, decrease my exponent by 1, 99. This is the derivative of the function x to the 100th. Okay? Easy. But those two examples are the simplest in these 6, because the other ones don't immediately look like a power function, but each one of them is. We just need to put it in the correct form. So for example, y equals 1 over x to the 6th. I would want to rewrite that as y equals x to the negative 6th power. Okay? Now that it's in the form of a power function, I know that my derivative, y prime, would look like this. Negative 6 x to the negative 7th. Careful with negatives, right? I'm subtracting 1 from negative 6. That would be negative 7. I could then put this back in the form of a rational function, but I don't really see the point. I'm just going to leave it in this form. D. What's the derivative of y equals the square root of x? Well, I mentioned that one earlier. It needs to be rewritten in the form of a power function, which is x to the 1/2 power. This y prime is going to equal 1/2 x to the negative 1/2 power. Okay? I believe, I'm not 100% sure I'm remembering this right, but I believe in section 2.8 we actually proved this derivative. It might have even been in 2.7, but we just said find the derivative for all a greater than 0 or something like that. And we ended up with something that looks like this, 1 over 2 root x, or root a, if that was the example I'm thinking of. These are the same function, right? If you know how to deal with rational exponents and then multiply to 1/2, that's the same thing. So I could have left it in this form, but I wanted to put it in this form for that example to connect it with what I'm pretty sure we did in the previous section. E. For part E, I'm looking at y equals 1 over the cube root of x to the 8th. Looks complicated, but really that's the same thing as x to the negative 8/3 power. That's exactly what this is equal to. So putting it in the form of a power function allows me to use the power rule. y prime is equal to negative 8/3 x. Subtracting 1 from this, 1 is the same thing as 3/3, so you need that common denominator. That would give me negative 11/3 as my answer. Okay? Finally, f, y equals x to the square root of x. Notice this is the same thing as x times x to the 1/2 power, which is the same thing as x to the 3/2 power. So I would rewrite that as y equals x to the 3/2 power, and then use my power rule. Y prime is equal to 3/2, bring the exponent down, times x, subtract 1 from the exponent to the 1/2 power. We just did 6 derivatives, which would have been, these would have been very, very complicated to do, most of them, actually just about all of them, with the limit definition, but we were able to knock them out really, really quickly. That's, no pun intended, but that's the power of the power rule. Okay, pun kind of intended. All right, come back to that. So we now have some useful techniques for taking the derivative of certain types of functions, and we're going to expand on this a whole lot more. But before we do that, I want to introduce the concept of a normal line. So normal lines don't show up as often in applications as the tangent line. We're mostly concerned with the tangent line in calculus, but the normal line is still something that shows up occasionally. We should talk about it. So if a function f of x, the blue curve here is what we're thinking of as f of x, y equals f of x. If it's differentiable at a number a, and if c is the curve given by that function, then we define the normal line at to c at the point a f of a to be the line that passes through a f of a and is perpendicular to the tangent line to c at a f of a. That's very wordy. So basically, in the image, what we're looking at is if you have a curve and you specify a point on that curve, and say you know what its tangent line is, the normal line to that point is another line that also passes through that point, but is perpendicular to your tangent line. So these form a right angle, okay? So let's do an example where we want to find both a tangent line and a normal line. Find the equations of the tangent line and the normal line to the curve y equals x to the 3/2 power at the point 4, 8. Now we actually just differentiated this function. Y prime is equal to 3/2 x to the 1/2 power, or equivalently, if you prefer radical notation, 3/2 times the square root of x. Okay? Remember, the purpose of a derivative is to find the slope of a tangent line. And since we're looking at the point 4, 8, if I want the slope of the tangent line to this function at that point, I would be plugging 4 into this derivative. So slope, I'm going to say mt. The t stands for tangent line. mt, my tangent line slope, is going to be equal to 3/2 times the square root of 4, which is equal to 3/2 times 2, or simply just 3. Okay? Now, I could go straight to the equation of my tangent line. It would be pretty easy to do that from here, but let's also think about the normal line before we do that. The normal line passes through the same point as my tangent line, but it's perpendicular to it. And if you recall from algebra, if you have two lines that are perpendicular to each other, then their slopes will be opposite reciprocals of each other. So the slope of my normal line, which I'll just call mn, would be the opposite reciprocal of 3, negative 1/3. Now I can find both lines very easily. My tangent line is going to have an equation of y minus 8 equals 3 times x minus 4. Notice this is point slope form for the equation of my line. Normal line will have an equation of, again, y minus 8 equals negative 1/3 x minus 4. Notice the only difference between these two when I have it in point slope form like this is the slopes. Because they both pass through the same point, they're both going to have a 4 and an 8 here and here. So that's it. That was not that bad, right? Most of the work in this problem would have come from finding this derivative if we didn't have the power rule. But now that we have this rule that makes finding that derivative so much easier, problems like this take substantially less time. Okay? Let me cover a couple more useful differentiation rules before we end this first video. So what we're doing right now is we're moving from specific types or classes of functions, like constant functions or power functions, and covering a couple of rules that apply to more general functions. So notice I'm saying here, if c is a constant and f is a differentiable function, I'm not saying what type of function f is, I'm keeping it general. Simply saying that it's differentiable. Then the derivative of a constant times f of x is equal to the constant times the derivative of f of x. In other words, you can pull that constant out and just differentiate f of x, then multiply the result by that constant you pulled out. Okay, and we'll do examples with this, but let's go through a proof. The proofs that I'm giving here are all straight out of your book, so you can refer to that too. But let's define the function g of x to equal c times f of x. Then what is g prime? Well, g prime is equal to the limit as h approaches 0 of g of x plus h minus g of x all over h. That's just your definition of the derivative. Now we use the definition of g here and here. G of x plus h is the same thing as c times f of x plus h. Minus g of x would be minus c f of x. So here's our definition of that function. Now we're going to use a limit law here. So the limit law is the one that allows us to pull a constant outside of the limit. Notice I could factor the c out of each of these terms here. I could factor that out of my numerator and then bring it clear outside of the limit because of the limit law that allows me to do that. So here's where it's being brought outside of the expression, and here's where it's being brought outside of the limit. Now what's left in here is simply the definition of the derivative of f. So this entire limit here can be written as f prime of x, and that's what we were after the whole time. So really, at its core, this property, this constant multiple rule for differentiation, is a direct consequence of the similar looking limit law that we've already covered in 2.3. Okay? We'll do one more and then we'll wrap up this first video. The sum and difference rules. So in this case, what we're looking at are also general functions, f of x and g of x, but this time we're looking at a sum of two functions or a difference of two functions. And what each of these rules basically says is that differentiation, the d dx operator out here, sort of has a property similar to the distributive property. I can distribute this d dx into each function here, which basically says that the derivative of a sum of functions is equal to the sum of their derivatives. That's a way of saying that. Same thing here. The derivative of a difference between two functions is equal to the difference between their derivatives. So we're going to just prove the sum rule here and then show that the difference rule is a consequence of the sum rule and the constant multiple rule. So we're going to define a function, capital F of x. It's equal to the sum of these two functions, f and g. Then what, by definition, would capital F prime look like? Well, here's your definition of the derivative. But by the way that we defined capital F of x plus h means little f of x plus h plus g of x plus h. Similarly, capital F of x over here is the same thing as f plus g. You need the brackets around those. Okay, now there's going to be some rearranging of terms. So notice if I were to distribute that minus in and then regroup some things, I would have f of x plus h minus f of x. I'm going to take those two terms, group them up, and then push them out into their own fraction here. Okay, so what I'm left with is g of x plus h minus g of x all over h here. And you should be able to see with relative ease that you could add these two together to get back to this step. Okay, now I'm going to use my limit law for sums to bring this limit into each of these expressions here. So limit of the first quotient plus the limit of the second quotient. And each of these is the derivative of f here or g here, both of which we assumed existed because we assumed that these are differentiable functions. So this would be the same thing as f prime of x, this is the same thing as g prime of x, and that's what we were ultimately trying to prove in the first place. For the difference rule, we don't need to go through another argument like this, even though we could. We could simply rewrite f minus g as f plus -1 times g apply the sum rule to this, and then the constant multiple rule when evaluating the derivative of this second term here. I'll let you think through the details of that. It's fairly straightforward. Okay, that's enough for this first video. We'll go ahead and stop here.